and have widespread electric vehicles. And in order to do that, we really need to change the chemistry in a lithium-ion battery to something different. And I'll tell you about how we're trying to do that today. So just to get us all on the same footing, I'll teach you about how a battery works, and then I'll tell you about some of the materials that we're working on in order to go beyond lithium-ion chemistry. So batteries are relatively simple electrochemical devices. They're formed of three components: an anode, an electrolyte, and a cathode. The anode electrode is where an oxidation reaction occurs, where electrons are basically released from this electrode. The cathode is where a reduction reaction occurs, where electrons are consumed. And the way that this is spontaneous, or the driving force for this reaction is the electrochemical potential difference of those two reactions in the two electrodes. So the electrochemical potential of the anode electrode is very high and it's very low in the cathode. And so it's energetically favorable for those electrons to flow downhill from the anode to the cathode. But in order to make that a source of energy for us to use, we need to separate these two electrodes with an electrolyte. So the electrons don't simply short from one side to the other. So the electrolyte acts to be an electronic insulator, but it allows for the ions to flow for charge compensation as you change the formal oxidation state of these two materials. So if I have the battery in this sort of geometry where there's no pathway for the electrons to flow because you can see this external circuit is broken, then nothing will happen. But if I put a load here and allow the electrons to flow from the anode to the cathode, then it can power your light bulb or your car, or whatever you're using. And that's how a battery stores charge. So of course, you can imagine there's a variety of different reactions you could use for the anode and the cathode, and there's a variety of different materials you could use for the electrolyte. And so this is really a big playground for chemists in order to sort of develop new materials and phases that go into this cell. And the type of chemistry that sort of revolutionized the way that we store charge is called intercalation chemistry. And so I'll describe that to you here. So the original material that was used is titanium disulfide. So this material is octahedral titanium in these sheets, and there's a van der Waals gap between them. And if you reduce this material in the presence of lithium, then you can add an electron to titanium. And then there's a lithium that goes in between those sheets for the charge compensation mechanism. And that reaction is very reversible, and I'll show you that in a second. But the thing that I really want to get across here that's sort of shocking here is that I can get one equivalent of lithium into TiS2. So I can form LiTiS2. And if I do that, if I look at the atom positions for LiTiS2 and I compare them to the delithiated phase, what you can see is that there's a very small change in the structure as a result of incorporating a full mole equivalent of lithium. So that's incredible, right? So this is the intercalation chemistry. There's a crystallographic similarity between the lithiated and the delithiated phases. And so that makes these reactions extremely reversible because the atoms aren't really moving around. It's only the lithium moving in and out of the phase that's allowing this to happen. And so we can do the lithiation reaction, we can do the delithiation reaction. And when we do that, the charge compensation mechanism is formally assigned to the metal. So what you want to think about is basically metal oxidation and reduction. So titanium 4 reduced to titanium 3 and vice versa. And that's how we think about where those electrons are going. So we don't use titanium disulfide in commercial cells, although this is the material that Stan Whittingham won the Nobel Prize for. Instead, they're metal oxides. So this is an example of a metal oxide that's used. This is lithium cobalt oxide just for simplicity. But now commercially, if you take cobalt and substitute manganese and nickel, you can get much higher capacities to yield these so-called NMC materials, so nickel, manganese, cobalt, and these are the commercialized type materials. So I just want to show you what those look like here. But the operation principle is the same. Lithium shuttles in and out between these van der Waals gaps, and you get reduction oxidation of those transition metals. Okay, so lithium-ion batteries have revolutionized our lives, enabled portable electronics, EVs, and they've also really been enabled by the chemistry, which was recognized by the Nobel Prize in 2019. So why am I looking at beyond lithium-ion batteries if they're so amazing? And that's sort of detailed on this slide with a focus on the cathode materials. So one reason is the cost. Lithium-ion batteries are pretty expensive. If you look at the cost of an EV battery, 75% of that cost is in the materials. If you look at the materials cost, most of that cost is actually in the active cathode material, so in that NMC oxide that I showed you. Resources is another issue that we're working with. So cobalt is primarily mined in the Democratic Republic of the Congo in a copper vein in the south part of that country. There's several child labor issues associated with cobalt mining and adverse health effects. So we'd really like to get away from cobalt. And then lastly is capacity. So although this intercalation chemistry works really well, we're nearing our theoretical capacity limits for that type of charge storage mechanism. So to sort of demonstrate that, here I have a timeline of materials that have been developed for intercalation chemistry since Stan Whittingham's LITIS2 in 1976. So John Goodenough came out with lithium cobalt oxide in 1980, and that was the material that was commercialized by Sony in 1991. And then we have since substituted cobalt for nickel and manganese, like I was talking about previously, to yield the NMC materials that were developed in 2003. And since in between these two, there have been other phases that are notable. So we have these lithium manganese oxide spinels and the lithium iron phosphate olivines. You may have heard about these if you're following the EV news. We can talk about that. But if we think about how much charge they can store, which is given by this ridiculous unit milliamp hours per gram, which is just number of electrons per unit mass, that's all that is. And we look at the theoretical, which is in orange versus the theoretical, which is in white versus the experimental, which is in orange, you can see that the NMC materials are reaching theoretical capacity. So if we want to store more energy and have lighter weight cells or lower volume cells, we're not going to be able to do it with intercalation chemistry. And in fact, if we think of theoretically the best material we could think of, we're really hitting a ceiling of about 300 milliamp hours per gram for this intercalation limit. So in order to go beyond that, we need to think of new mechanisms. So one mechanism that we've been really interested in is a mechanism that's shown by lithium-rich materials. So the conventional intercalation materials are shown on the left, where you have one lithium per metal. So theoretically, you could remove one lithium per metal, which would be one electron per metal, right? If we go to lithium-rich materials, where now we substitute some of the metals in the metal layer with lithium, so you can get to stoichiometries that look like this using heavier metals like ruthenium, then you can think about oxidizing two lithiums out of this material, which would mean 2 electrons per metal. And so where do those electrons come from? You can imagine you could do a 2-electron oxidation on the metal if you had a metal that could do that. Or you could start to access the p states of the anion and start to actually pull electrons out of those p orbitals of the oxygen, for example. And so this is a really exciting area where we're trying to do so-called anion redox, access electronic states given by the anions to increase the theoretical capacity. And just to demonstrate the kind of numbers that you would get in oxides, if you compare a 1-electron process with a light metal cobalt to a 2-electron process with a heavier metal ruthenium, you can get a much higher gravimetric capacity because you're storing more electrons. Okay, but oxides are sort of an issue, and hopefully this works. We shall see. Oh, you can't hear it. Well, you'll have to read it. Okay, so maybe I'll read it to you. This is my student Ishan, who wrote this beautiful poem about why we don't like to do anion redox in oxides. So he says, if you wish to oxidize anions, you see, it's hard to do with oxides like lithium-rich NMC. The voltages swell, but in case you can't tell, the electrolyte decomposes vehemently. And he does it much better than I do. But so the problem with trying to access p states of oxygen is that they're very high voltages or very low energies. And so you'll start to decompose other things in your cell before you do any oxide oxidation. And so that has really motivated us to go to sulfides. So over here on the left, we have our oxide paradigm. If we think about doing sulfides, sulfides, the p states are much lower in voltage or higher in energy than the oxygen p states. You're going down the periodic table in that chalcogen column. And so the p states lie well within the electrolyte stability window. Keep in mind, this is on a voltage scale, not an energy scale. And so we can access the sulfur p states without decomposing the electrolyte that it's in contact with. And that's a huge benefit when we're thinking about doing mechanistic studies or even doing something that can be reversible. The other benefit of the sulfides is that now we can do lithium-rich metal sulfides with lighter metals like iron. So lithium-rich metal sulfides like Li2FeS2 are known, and iron is a really great metal to use for a sustainable battery chemistry. So if we compare the natural abundance of iron versus cobalt and nickel, of course, it's much, much higher than both cobalt and nickel. And being in Arizona, I have a picture that I actually took in Sedona. So all of the red that you see in Sedona is due to hematite, iron oxide. So there's a lot of iron, especially domestic iron, that we could have access to if we had an iron-based cathode material, which would be great to get away from things like cobalt and nickel. But if we're thinking about criticality, we also have to think of other things beyond just natural abundance, right? So criticality has many, many components that go into it. We have to think about things like geographical distribution, geopolitics, environmental and social costs of mining. There are all of these things that fold into this that make it very, very complicated. And while I don't have time to talk about all of this today, and there's not one single metric that defines this, we can have a very quantitative metric that defines geographical distribution, and that's this HHI index. So this Herfindahl-Hirschman index is often used in economics to describe how concentrated a market is. And we can use it when we think about resources by describing how concentrated that resource is throughout the world. So if I have an HHI axis now on the left, if it's a low HHI, then we consider that resource unconcentrated, meaning it's found all over the world. If it's sort of in the middle, it's moderately concentrated. And if it's above 2,500, we consider that highly concentrated. And this was all inspired from this paper in Chemistry Materials in 2013 that did this for the whole periodic table. So we can look at the HHI number for both the production and the reserve of each resource. And that's important when you're opening a new market for a material, because if you have new demand, you need to know what's there in order to access this new demand, right? And if we compare then iron, cobalt, and nickel, you can see that iron is much, much better as far as HHI compared to cobalt. And nickel, it's competitive with. So nickel, the problem with nickel is the cost. And so iron will be much less costly than nickel. And so we think iron is a really great sustainable metal to go after. The other benefit is that it's a domestic resource. If you look at the top 10 countries producing and have reserves in iron, you can see Canada and the United States in both of those lists. And so for those reasons, we're also very excited about it. The other reason we really like the sulfides is because of the electrochemistry. So now I'm going to show the electrochemistry of Li2RuO3 versus this phase, which is Li2FeS2. So this material is a little different than the metal oxide. So it has tetrahedral iron and it's split site with lithium. So you have a 50-50 chance of finding lithium or iron here. And these are edge sharing in the plane. And then you have octahedral lithium sites that are very similar to these. And these two are shown to scale. So you can see the difference in the size of their unit cells. So if I look at the electrochemistry, what I'm doing here is for the charge curve, I'm oxidizing the material, applying a constant positive current and watching the voltage change as a function of stoichiometry. And then this curve is the discharge curve where I'm reducing the material, applying a constant negative current and watching the voltage change as a function of stoichiometry. And the big difference that you can see between these two phases, they both get multi-electron, which means they both have more than 1 mole of electron per formula unit. They're both getting around 1.75 or so. So that's great. The big difference is in how reversible the electrochemistry looks. So without knowing anything about the electrochemistry, you can see that the cycle 1 and cycle 2 charge curves of this material are very similar. And the cycle 1, cycle 2 charge curves of this material are very dissimilar, right? So that tells you right away that this material, when I charge and discharge it, looks nothing like what I started with, because the electrochemistry is telling me it's different. And this material seems to be very reversible. So why is that? And so we can go through and try to characterize what's going on with the Li2FeS2 and understand, one, how are we getting 1.75 electrons out of this material when we have iron 2 in a sulfide? And then two, why is it beautifully reversible in a sulfide and not in an oxide? And so the work I'll tell you about is largely due to these 5 people on this slide. So Andy Martinolich, Charlie Hansen, Steve Kim, Ishan Patheria, and Josh Zach did most of the work that I'll tell you about. So I definitely want to highlight them from the beginning. And the first thing we wanted to do was understand the charge compensation mechanism. So how are we getting 1.7 electrons out of this material? Where are those electrons coming from? And in order to do that, we turned to X-ray absorption spectroscopy. So these are all K edges. So we're going to look at the iron K edge and the sulfur K edge as a function of charge and discharge and determine what's being oxidized and what's not. And so the iron K edge looks something like this, but we can just look at the position of the rising edge, which tells us something about the formal oxidation state of this metal. And to do that, we can look at the derivative. So it's much easier to tell the position. And so that's what we'll show up here. So this is just for the pristine material. And then for the sulfur K edge, you have this beautiful pre-edge feature in the sulfur K edge. And then this is the rising edge here. This pre-edge feature comes in because you have a covalent iron sulfur bond. And so you get a really nice, beautiful pre-edge feature. And this has been characterized sort of in great detail by people that look at metalloproteins, looking at iron sulfur clusters and things like that. Okay, so if we look at the oxidation, so down here will be our sort of map of where we are in oxidation and reduction. So the first thing we're going to do is oxidize to this point here. So we call this the sloping region. So this is where we get about half an equivalent of electrons out of the material. And if we oxidize to that point, what we see is a shift in the iron K edge, which suggests oxidation of iron. So we have oxidation of iron 2 to mix iron 2, 3. And then in the sulfur K edge, we see an increase in that pre-edge feature, a drastic increase in that pre-edge feature, which is because as you oxidize iron, you're going to get a more covalent iron sulfur bond. And so that pre-edge feature will go up. And so that's exactly what we see in the sulfur K edge. Okay, so that makes a lot of sense. We're all good now. What's really interesting is that if we oxidize to 3 volts, which is that 1.7 electron part, then the iron K edge doesn't shift at all. We've taken an entire electron out of this material. The iron knows nothing about it. If we look at the sulfur K edge, though, you see a huge change in the spectrum. So you see a new pre-edge feature that comes in, and you see a massive shift in the edge. And so this is diagnostics of oxidation of sulfur in this material. So oxidation of sulfide to something else as a result of this process, this electrochemical process that we're doing, which is a really nice confirmation that we are doing anion oxidation in these materials. So why do we get a new pre-edge feature here? Well, we can compare this with a standard, which would be FeS2. So the fully oxidized material would be FeS2. If I were to do this, if I just pulled lithium out, I would get FeS2 stoichiometrically. The thermodynamic phase that's the most stable in that stoichiometry is pyrite. So we have, in that phase, we have octahedral iron, and all of the sulfurs are persulfide. So they're S2 sulfur bonds in pyrite. If we look at the pyrite X-ray absorption spectrum, we see a massive pre-edge feature here that overlays almost perfectly with what we measure in our oxidized material. And so we think that this is really good evidence that we're actually getting sulfur bonds in this material. Whether or not we're getting octahedral iron, I'll get back to in just a minute. So just to summarize, this first region is oxidation of iron to iron 2,3. And then the second region is really sort of localized on the sulfur. So we're getting oxidation of sulfide to persulfides. And we can reduce this material. So we do the reduction, and we see what we would expect based on the electrochemistry, which is that everything should basically go back to where it was in the beginning of this pristine material. So we see the iron edge moves back to its original position. The sulfur K edge also moves back. For the most part, this pre-edge feature goes away. There is a slight increase here that is different. And there's differences in the XFs, which we can talk about later. But spectroscopically, for the most part, we're oxidizing it and then we're reducing it, and it's very reversible. So if we were to sort of simplify this, we can plot the positions of those edge features as a function of the electrochemistry. So this will become useful later. So I'm just going to normalize or shift everything to 0. So if I look at this sloping region, first I get a huge shift in the iron edge, which is shown by these open circles. The sulfur edge shifts a little bit because it's not a perfectly ionic material, so that makes sense. But then in this plateau region, we get no shift in iron and a huge shift in sulfur. So it's basically this sort of sequential oxidation mechanism. And then they both shift back to their original positions. So what allows us to access these sulfur P states in this high plateau region as a result of this initial oxidation? So to think about that, we worked with Anton van der Ven at UCSB, who did some partial density of states calculations for us. And here's the partial density of states of the initial material. And so you see at the Fermi level, you have a high density of iron D states. So it makes sense that when you oxidize this material, you're going to access iron D first. When we partially delithiate this material, we model it very similarly to the pristine material based on some X-ray diffraction. And we just assume that we're forming lithium vacancies. And if you look at the partial density of states of that material, you see that the sulfur P states have pushed up closer to the Fermi level. And that's as a result of a rehybridization of the iron D and the sulfur P states to form a more covalent iron sulfur bond that you see in these electron density maps. So this higher covalency actually pushes the sulfur P states up, and that's what allows us to access them in sequential oxidation steps. So what happens to the iron when we start to do this? I mentioned that the thermodynamic phase is pyrite, that's octahedral iron. Are we actually converting to pyrite, or are we doing something else? So to think about that, we looked at the XFs. So this is a local structure probe that we can look at the first shell correlation of the iron species, and we can look at the bond lengths, and we can also look at the coordination number. And so the bond lengths are plotted here, and the coordination numbers are plotted here. And again, I'm plotting everything on top of the electrochemistry. So you see in that initial oxidation, the iron sulfur bond length decreases quite a bit, which makes sense. We have a more covalent bond, we've oxidized the iron. But what's really amazing is that in this this next oxidation, where we get 1 electron, the iron, both the bond lengths and the coordination numbers stay about the same. So even though we're pulling 1 electron out, we're forming persulfides, the iron local structure knows nothing about it. It's staying tetrahedral, it's not really migrating according to the XFs data. And so the hypothesis that we came up with to explain that is this tilting mechanism. So if you think about this material as looking something like this when we oxidize it, the lithium can be removed from here or from here. We see that from DFT calculations, it's a little bit more favorable to be removed from the tetrahedral sites, but we're removing more than 1 mole equivalent, so it doesn't really matter. They're coming out of both sites. So if we remove from the tetrahedral sites, we go from what was edge sharing to now corner sharing tetrahedra. And those corner sharing tetrahedra, we think, can now distort within the metal layer to sort of corrugate and maybe form a new sulfur-sulfur bond here. So that's where we think these new sulfur-sulfur bonds are. We've been collaborating with Andrew Morris at the University of Birmingham to simulate some of these X-ray absorption spectra to confirm or deny our hypothesis or provide support. What we see, so they've been able to replicate the pristine X-ray absorption spectrum quite well. So this is the sulfur K edge. And then if they throw in a sulfur-sulfur bond due to this sort of tilting of the tetrahedra, then they see the evolution of a new feature in the sulfur K edge that correlates pretty well with what we see in the experimental results. So we actually think that this is a pretty diagnostic feature associated with these new sulfur-sulfur bonds. So just to summarize the mechanism of this material, the first oxidation is localized on iron. So we do about half an equivalent. We get mixed iron 2, iron 2, 3. The structure is very much the same when we do that oxidation. So this is very similar to just intercalation chemistry. But then the next oxidation, this 1 electron oxidation, comes from sulfur. So we're doing sulfide to persulfide. And that causes structural distortions in the material that breaks a lot of long range order. I didn't show you the diffraction, but you'll just have to take my word for it. Breaks a lot of long range order and causes these metal layers to corrugate within the layer to form those new sulfur-sulfur bonds.
What's the tilting?
Well, we don't know. We're not able to measure it. Yeah. We're trying to do that with PDF now. I'll let you know if it works. So one property that we've been really interested in understanding is how covalency plays into the ability for us to do anion redox. So in the oxide literature, there have been many, many papers. This is a non-exhaustive list of people who have suggested that covalency plays a really important role of doing anion oxidation. Now that we have a material that definitely does sulfide oxidation, that we definitely see redox on the sulfur, we can tune it in order to sort of probe how covalency plays into the mechanism. And the way that we did that is through anion substitution. So if you think about the sulfide, we can move down the periodic table and substitute a selenide for the selenium for the sulfur. That pushes the p states up in energy and gives you greater orbital overlap between the iron D and the selenium p states. And so that should give you a more covalent material. And what we found is that we could make the Li2F the Se2 material. It's isostructural to the sulfide, which isn't too surprising. So selenides and sulfides usually are isostructural. But because these two materials are isostructural, we can make the entire solid solution in between. So it's an anionic solid solution where I can have some statistical distribution of sulfur and selenium on the anion site, depending on my input stoichiometry. So that allows us to systematically tune the position of the P levels versus the D states and essentially tune the covalency. And if we do that, what we see in the electrochemistry is quite amazing. So in the maroon trace, this is the sulfide, and in the blue trace, this is the selenide. And everything in between is the solid solution, so some distribution of selenium and sulfur on that anion site. And what you see is that this plateau associated with anion redox systematically shifts to lower voltages as a function of stoichiometry. And I can actually plot that voltage versus stoichiometry and find that there's basically a linear correlation. So that's just, it's amazing because what you might have expected is that first you see a selenium plateau and then you see a sulfur plateau because you have both anions in the material, but you don't see that. And the reason is because you have perfectly mixed bands because you're oxidizing from an extended solid. And so the bands have selenium, sulfur, and iron character, and you're just systematically moving those up and down by shifting where the p orbitals are that you're mixing into that band. And we can measure that directly with the electrochemistry. And so how does that play into the charge compensation? So I've already shown you this plot up here that shows basically the position of the edges on top of the electrochemistry. So now we can make this a little, add some more dimension to this. So if we look at the selenide, so now the selenium edge I'm showing in orange, you can see that the iron states shift throughout the entire charge and the selenium states are shifting throughout the entire charge because we have a more covalent material. So as we oxidize, we basically push the charge compensation back onto the metal instead of just pushing it onto the anion. And if we look at the mixed material, we see that they're all shifting throughout the entire oxidation process because we have selenium, sulfur, and iron character in those bands that are right at the Fermi level. So this was just a really nice demonstration of what happens when you change the covalency in this way. The other thing we've been able to do, and here's another poem you're not going to be able to hear, so I'll read it to you. So sulfide voltages are often very low, and that's why they're not commercialized. And so Ishan's going to tell you why we're still interested in sulfides. So the voltage of sulfides is too low. They were model systems long ago. While the voltage is around 3, have you accounted for gravimetric capacity? The energy density is beyond anything we know. So there's some artistic freedom in here. It's not quite 3, and it's not beyond anything that we know, but it is a low voltage, and we can get very high gravimetric capacities out of these materials because we can do this multi-electron oxidation. So despite the low voltage, because we're getting 2 electrons and it's reversible, that makes them actually very competitive. So the column you want to look at here is the energy density. So this is watt hours per kilogram, which takes into account the capacity and the voltage. And if you look at the energy density of Li2FeS2, it's about 833. If I compare that with the NMCs, it's comparable to commercialized oxide materials, but now we're using iron, which is a much more sustainable metal. If we compare it to lithium iron phosphate, which several companies are now touting for next generation batteries for their EVs, it's much, much better than lithium iron phosphate. So it's better than the best iron containing material. And Ishan has been able to make a new lithium rich sulfide material that hopefully we'll publish soon, that has an extremely high energy density. So we can get this even higher, and we've done that by increasing this number here, the gravimetric capacity. So we're really excited about that. See if I can get it. Okay. So I mentioned that we have a mechanistic hypothesis that vacancies are correlated to the anion oxidation process. I usually get to drink when Ishan tells you his poems, but so I mentioned that this tetrahedral tilting is enabled by the presence of that vacancy that gives you the corner sharing network. So we wanted to probe this experimentally to determine if vacancies were indeed a structural motif that's required for the formation of a sulfur-sulfur bond. And in order to do that, if you step back and think, okay, well, what experiment would actually prove that? Well, you would have to have a material where when the cationic sublattice is fully occupied, it doesn't work. There's no capacity. And when you introduce vacancies, you get anion oxidation. That would be the experiment, right? In order to realize this, you need a material that has no transition metal redox. Because if you have transition metal redox, then you will never see this part, right? Where you have a fully packed cationic lattice and no capacity. Because if you have transition metal redox, you'll form vacancies by lieu of oxidation of your metal. And so you'll always see capacity and you'll never know why it's there. So we set out to set a materials system that gave us these 2 conditions. And we had to go away from the lithium iron sulfides, and we went to lithium titanium sulfides. So there's a lot on this slide, but I'll walk through it. So on the top right here, this is LiTIS2. This is a material that's similar to the one that I showed you before. If you oxidize this material, you get oxidation of Ti3 to Ti4, and then this plateau is suggested to be sulfide oxidation. Okay, so this material doesn't work because we have Ti3 in it, right? I can substitute lithium for titanium. So if I take 1/3 of the titaniums and put in lithium instead, then the formal oxidation of titanium goes to titanium 4+. So just think of that as very similar to Li2RuO3, except in the sulfides. So if I do that, then you see that the capacity is basically nothing. So this material has a fully packed cationic sublattice. It has a D0 metal, titanium 4, so we can't do transition metal oxidation. And it basically shows no electrochemistry when we oxidize it. So this could act as our negative control. This is our material that acts as our no capacity material. And the stoichiometry that I'll show, we're going to do a lot of substitutions on this, so I'll just walk you through it a little bit. So before the parentheses, this is the lithium concentration in the lithium layer. And then in the parentheses, that's the distribution of lithium and titanium in the metal layer. So we'll do a lot of substitutions, and I'll try to use this formalism as we go through. So to prove to ourselves that that this is due, that this region is due to titanium oxidation, and that we can systematically change the oxidation state of titanium, we made, let's see, okay. So we were able to substitute. We were basically able to take lithium out of the lithium layer and form vacancies. And by doing that, we'll change the formal oxidation state of titanium. So if we do that, so here's our fully packed cationic sublattice, but now I've only replaced 1/4 of the titanium with lithium. So it's not titanium 4, it's a little bit lower oxidation state. So we can actually do oxidation of titanium. And we see that that region grows in the electrochemistry. If we take out a little bit of lithium from this phase, then we introduce vacancies, but the titanium oxidation state goes up. And so we see the contribution from this initial region go down. So that's good evidence that that's what that is from. And if we go up close to titanium 4, but not quite, you see that this has gone down quite a lot. So that tells us that this initial region is due to titanium 3, titanium 4 oxidation. And for anybody doing electrochemistry, what's really interesting here is that I can correlate the open circuit potential, which is an extremely easy measurement to make, with the formal oxidation state of the titanium, which is kind of cool. So all you need to do is measure the OCV, and I can tell you what the oxidation state of titanium is in your material without any spectroscopy. So that's kind of a cool feature of electrochemistry. Okay, so now we know that we can tune the titanium oxidation state, we can form vacancies in this metal layer, and we can systematically probe this material. So now we need this sort of correlation between the fully packed cationic lattice versus a lattice that has a vacancy in it, but has D0 titanium. So to do that, we can do this substitution, where we substitute titanium for lithium, and we control the stoichiometry very carefully so that the titanium remains 4+, but we still introduce vacancies, and we can do that in this way. And to prove that we have vacancies in this material, it's often very hard to do that, but we can do it. We've done it a variety of ways, including various stoichiometric analyses, but we can also do it electrochemically, because if you think about it, this material has a vacancy where a lithium could go into. We have titanium that can be reduced. So we can actually directly probe the presence of vacancies by just reducing this material first. And if we do that, so here's a reduction in a lithium electrolyte. So we're putting lithium in. This number should correlate to the vacancy concentration. We think we have 0.25 moles of vacancies. We get a number of 0.26 here. So it's very, very close. So that's telling us we can put 0.26 moles of lithium into this material, telling us we have vacancies. We can go one step further and use the divalent ion like magnesium. If we use magnesium, then for every magnesium, we should get 2 electrons. So for every vacancy, we should get 2 electrons. So this number should double. And it about doubles. It's about 0.47. So there's some kinetic limitations here that prevent us from fully magnesiating the vacancies, but it's very, very close. So this is just a really nice probe to show that we have vacancies in the material. And so now the question is, do vacancies turn on anion oxidation? That's what we wanted to probe initially. And so if we look at the vacancy concentration, so here's a vacancy of 0. We see what sort of the control case where you get very little oxidation. When we start putting vacancies into this material, all we're doing is changing the vacancy concentration, keeping the titanium oxidation state at 4+, which means that there's no sloping region. It basically goes straight to the anion redox plateau. We see the anion oxidation just turn on as we put vacancies in this material. So this really does suggest that vacancies are necessary in order to do anion oxidation. We've confirmed that the charge compensation mechanism is on the sulfur. So here's the titanium K edge. You can see it doesn't shift from pristine to full charge. And if I look at this is just a titanium 4 reference. If I look at the sulfur X-ray emission spectroscopy, this is the K beta and the K alpha. From pristine to full charge, we see this shoulder growing. This is indicative of sulfur oxidation. So TiS3 is material that has sulfur dumbbells in it. And it looks like it's approaching sort of what TiS3 looks like. And we can look at a shift in the K alpha emission. We see from black to orange does shift. So that does suggest that we're doing sulfide oxidation. Okay, so what have we learned about sulfide oxidation so far? We know that sulfide oxidation forms sulfur-sulfur bonds as opposed to just holes on sulfur. So once you depopulate these p orbitals, they rehybridize to form a new bond. Vacancies, we've shown that vacancies enable the sulfur-sulfur bond formation. And the way we think about that in the Li2TiS3 phase is that the sulfur-sulfur bonds actually pinch along the octahedral edges that are neighboring a vacancy. And they wouldn't be able to do that if there were metal correlations there. We've been able to tune the crystal chemistry to adjust the charge compensation mechanism. And we've been able to tune the covalency, which also shifts the charge compensation mechanism. And that also allows us to tune the voltage by shifting basically where the P states are relative to the D states. Okay, so where does this sit in the whole slew of battery chemistry? And how do we think about this sort of from if we take a step back from other materials that have been developed? So on the top here, I have the average redox contribution per sulfur. So over here, this would be no anion redox. And over here, this would be 2 electrons per sulfur, which would be a lot of electrons on sulfur. So on the left, you can think about this as sort of intercalation chemistry, where by virtue of non-ionic metal anion bonds, you get some contribution from sulfur, but not a lot. And so you get very structurally similar materials as you oxidize and reduce, but this is lower capacity. On the other end, where you have 2 electrons per sulfur, you have very, very drastic phase transitions that occur. So this is sulfur chemistry, if you're familiar with this, lithium sulfur batteries. So this is lithium sulfide converting to sulfur. Those phases are very, very different. So you get massive volume changes. The mechanism is very complicated and it's not very reversible, but the capacity is extremely high. And so the way we think about these materials is somewhere in between, where you have contributions from both the metal and the anion. And that allows you to have a higher contribution from the anion, giving you higher capacity, but you still have the metals in there that keeps basically glue the material together as you oxidize and reduce. And so it's much more reversible than this case. So that's how we think about this. And we think that sulfides are the way to go, not only because of everything I told you so far, but because per sulfides are thermodynamically stable phases. So we mined the ICSD in the materials project to look at all materials that contain sulfur-sulfur bonds, which are around 2.1 angstroms. And they have all of the binary persulfides and the ternary persulfides here. And you can look at this for days, but just look at how many colors you see here, and you see that there are a lot of materials that have persulfides in them. If I compare this with peroxides, it's much simpler, right? So there's very little ternary peroxides, and the only binary peroxides are in these alkaline earth materials. And so the peroxides are much less stable than persulfides. So we think this is the way to go if we're going to target anion redox. Okay, so I told you about what my group does on cathodes and why we're trying to go beyond nickel and cobalt to use iron-based materials. I just want to very briefly mention that we have other projects in my lab. So we are very interested in solid-state electrolytes. We work on weird solid-state electrolytes that conduct things like magnesium and zinc and calcium instead of lithium. But we also work on lithium electrolytes, and we're working on other multivalent liquid electrolytes. And then on the anode side, we work on metal chemistry. So some of those multivalent ions that I told you here are only useful if we have a metal anode. And so we're very interested in that. And so just to highlight some things that we have coming out, we've been able to develop a new superionic lithium conductor. So this is a Li3BS3 phase that's substituted with silicon. And this came out of a semi-supervised learning approach that we developed that pointed us to this phase. And so we're really excited about that. And then in the ionics on the multivalent side, we've been able to show multivalent deposition and stripping from a solid state electrolyte. So this is a phase that we love, or I love, that we've been working on for a long time. We've been able to increase the conductivity of this material and actually show that we can deposit zinc from it, from a solid, which we're very excited about. And so I pointed out a lot of the people that contributed to this project throughout the talk, but we have a lot of collaborators as well that I didn't get to show any of their work today. And I've worked with a great group of postdocs and students and undergraduates as well. So I have to thank them for all their contributions, and thank you so much for listening.
Thank you so much, Kim. Do we have questions? Peter, yeah. Please.
Thanks for the nice talk. It's interesting. I've never really thought about anion redox processes. Can you go back to the slide where you were showing the substituting lithium into the titanium? You were showing how it changed the titanium oxidation state.
Yeah.
This
one?
Yeah, any one of these. So the idea is you're substituting lithium for titania and
Titanium for lithium.
titanium for lithium.
Yeah.
And so the oxidation state, the electron transfer is what then? The lithium is always going to be +1 and the titania is always +4, or does it? That's the part and also you always just showed S2 at the end. And when I see S2, I always think it is S2 minus, but I'm not sure if that's correct.
So these phases are all
yeah, this was the graph I meant, where you're showing the change in the oxidation state of the titania. I'm not sure I understood that.
Yeah. So the way that we make these materials, first we check the structure to make sure the structure is this sort of disordered rock salt phase. And if that's true, then we can assign 2- formal oxidation state to the sulfur, because we have no sulfur-sulfur bonds. They're all in this sort of, you know, this
Bonded to the
close packed flat.
Right,
Yeah.
Right.
So, so we checked that, make sure that's true. So we see no charge compensation by the sulfur as a result of the
Okay,
substitution.
maybe that, I see, any electron transfer is only between the cations. It's not involving the sulfur, is that correct?
So I wouldn't think about this necessarily as electron transfer. It's more of charge compensation by shifting the stoichiometry. So when we do this, you can have, the question is, do we have vacancies and have we changed the formal oxidation state of the titanium? And the answer is yes to both of those questions. So as we do the substitution, well, maybe it's easier to show, this is sort of a weird substitution that we did just to show that we can tune it. But in this case, if I take lithium out, I've taken out a positive charge. So that charge has to come from, well, that charge has to be compensated in some way. And in this case, it's compensated by the lithium. It goes up in charge.
So then I
Does that
was
make
having a debate with one of my DFT friends about the meaning of oxidation state and things like that. So locally, where the vacancy is created, the titaniums are either +3 or +4. Is that right or wrong?
So the
This
titanium,
is an average oxidation state, is that right? But it wants to be +3 or +4. So where you introduce the vacancy, what's the local environment around the vacancy?
I don't know.
Okay,
It's a good question.
yeah.
So the vacancy, this vacancy should be, it's a cation vacancy, so it's formally negatively charged, if you think about it that way. But so it's possible that the titanium that clusters around the vacancy might have a higher oxidation state than those that don't, but I don't know the answer to that question in these materials.
And then just one follow-up. So is the high level message that I should take away that if I want to have redox activity in anions, having cation vacancies is helpful?
Yes,
Okay, all right.
absolutely. Yeah. So the high level message is anion oxidation in a sulfide leads to new bonds, to sulfur-sulfur bonds. In order to form those bonds, you need vacancies. Yeah.
And that was the cartoon where you had the cation missing and the two sulfurs tilted together.
Yep.
Fine.
Yep.
Got it.
Exactly.
Just gonna read something from the chat, wait.
Yeah, sure.
Interesting talk. There's also charge compensation on the anions in the NMCs.
Yeah.
Seems to be more like a comment. Also, you're better off looking at L23 edges to measure charge state. Comment. I think your energy densities assume full dilithiation of the cathode. That might be a half question.
Well, it depends on which energy density. So the theoretical would assume full dilithiation. So the theoretical numbers that I showed. Yeah, so maybe they were talking about that Li2 RuO3 slide and the Li2 LiCO02 slide. Yeah, so those energy densities were assuming full oxidation, which is not always practical. So in LiCO02 and lithium cobalt oxide, you only get half the lithium out before you get a phase transition. So it's not possible to do that. That's why you have to substitute the metals. But yeah.
Okay.
Yeah.
Questions in the room? See anything right now? There's another question here in the chat. Can you speculate on the lifetime of the sulfide materials as well as the potential change in size compared to conventional lithium-ion batteries?
The lifetime is in the cycle life, probably, I would guess. Yeah, so when we're doing these structural transitions of sulfide to persulfide, that should be less reversible than just doing intercalation chemistry. So we're thinking about ways now to mitigate that. So one thing we're trying to figure out how can we stabilize the structure maybe without forming that new bond? Is that possible? Can we stabilize holes on sulfur basically? So we're working on that now to try and understand that. But these materials fade, but they don't fade horribly, and it's sort of difficult to say how bad they are because we need to do a lot of engineering on the electrode side in order to determine that, and we don't do that. So hopefully we're sort of working on that as a side project, but yeah, there's a lot of electrode and cell engineering that goes into figuring out capacity fade, so it's hard to say. But if you think about the structural change, it should be worse than the intercalation material. Yeah.
To make me happy, can you talk a little bit about the synthesis of how you make these materials? Just kind of briefly, since you didn't really touch upon that one.
Yeah, sure. They're all pretty straightforward. So they're from I think we use lithium sulfide instead of lithium. So lithium sulfide, titanium, and sulfur. Grind them up, put them in a sealed quartz ampule. That's, well, not quartz, sealed ampule, and then that's carbon coated. So we do a carbon coating for the most part to prevent reaction of lithium with the tube. and then heat them up to, I think these are like 950 or something like that. So just solid state. Yep.
There's another question in the chat on the super ionic conductors and their molecular level design in any of the composition spaces studied. Do you see any electron conductivity or just purely ionic conductivity?
Oh, yeah. So for lithium ion conductors, we definitely have to worry about electronic contributions. So we try to determine that by doing DC measurements, which isn't exactly the best method. So the nice thing about lithium is that you can do atomic characterization using nuclear NMR, so nuclear magnetic resonance NMR. So you can figure out what the diffusivity is that way, and that'll give you a really nice probe of how the lithium is actually moving. But all of these materials that are here are pretty wide bandgap materials that don't have a high electronic contribution. So the electronic contribution is like 5 orders of magnitude lower than the ionic. So then we just don't care about it.
Sense.
Yeah.
Another question in the chat, the trivia question: in your XF data fitting, does the X-ray source have a big effect on your interpretation of the bond length? Sorry, just paused. Bond length and structure.
The X-ray source?
Yes. Does the X-ray source for your XF's measurement?
Yeah, I mean, we do all the XAPS measurements at synchrotrons to
Yeah.
get high enough energy X-rays to get good resolution in the XAPS region. So the XAPS region is after the near edge. So you need enough resolution there to do the Fourier transform to get the XAPS. And so we do it all at beamlines. I think,
Which beamlines are you using? Just out of curiosity.
yeah,
Always
so
the same ones, or do you?
no, for the metal edges, we'll go anywhere. For the sulfur K edge, there's very few beamlines that can get that low because it's 2.5 EV, so it's KEV, so it's really low. So we go to SSRL usually for that when we get time there.
Yeah. Is it again, out of curiosity, do they have like a mail-in service, or do you send students there, or do you go there yourself?
They don't have a mail-in
Okay.
for tender, as far as I know. I think there are some beamlines at APS that are doing mail-in for X-ray absorption. Yeah.
I have maybe just a higher level philosophical question. It's actually based on your title, because when I saw 1 is the loneliest number, I thought you were going to talk about the fact that 1 electron transfer processes are really a lot harder than 2 electron transfer, but you didn't say that. Did you want to say anything about the title and why you had
Well,
1 is
some
the
sort of a
loneliest?
trivia question of who can name the band
I see. Okay.
for that song.
Yeah.
And we can name that band, I'll give you candy. It's sort of an old song, but no, so 1 is the loneliest number is more like the capacity. So you get much lower capacities when you do single electron processes, and if you go to multi-electron, you get much higher capacities, and everyone's a lot happier, less lonely. Yeah. No, 1 electron processes are a lot easier. Yeah.
Christina?
Oh. Krishna?
Yeah, sorry, didn't mean to. Kim, this.
God in the room. God is asking the question.
Kim, meet Krishna,
Can't wait.
at the University of Arizona, also known as
Hi.
godlike.
Shaking from the sky.
Krishna, hi. Do you have a question?
Hi. No, more of like Kim, you touched upon solid state electrolytes towards the end. I didn't fully understand, fully get it. Were you saying that you were developing a class of solid state electrolytes that are super ionic conductors for MgCa? Just the same material that allows for super ionic conductivity, or is there different materials for the different cations, for different ions?
Are you talking about between the different mobile ions, like between lithium,
Yeah.
magnesium, calcium, and zinc? Yeah, we're trying to develop solid state ion conductors for multivalent cations. So
Okay.
those are different materials than the lithium containing materials. Yeah.
Correct, but is it going to be the same material for the different cations, right?
No, different materials. So that's one thing
Oh,
we
diff-
found. Yeah, we found
Okay.
that if you try to superimpose a divalent cation onto a monovalent ion's conduction pathway, it's like a recipe for failure. So you need to
Okay.
develop a new material specifically for divalence in order to get it to
Okay.
work.
Yeah, so okay, that's what I
Yeah,
was.
so we've been developing these semi-supervised machine learning algorithms in order to predict new materials And that we started with lithium because there's a lot more known about lithium. And that led us to this phase, this Li3BS3 phase. And then now we're trying to push that forward to divalence.
Oh, good. Thank you.
Yeah.
I think there's another question on the chat, Christina.
Yes, I see it, Krishna. Thank you.
There are also more gods on Zoom.
Yeah, I think gods.
Bruno,
Do I need to kneel or?
what's up, Bruno? Oh, you just wanted to say hi. That's
I just wanted to say hi, make my presence noticed. I could have missed the opportunity.
yes, you have to do that absolutely.
Yeah, is Ankit missing?
No, I'm gonna say.
Ankit is embarrassed.
He's
Okay.
He's a mere mortal in the room.
And let me read out the last question. Sorry. So thanks for the talk. Would the synthesis route, chemical or physical effects, stoichiometry, capacities, etc., are these variables taken into consideration? How do you think they would affect the results? Love it. Synthesis.
So for the solid state electrolytes, the processing that we do post synthesis plays a huge role in what we measure. Like, in sadly huge role that makes us sad, very sad, because it's like you got to control everything.
Yeah,
And which, you know, it's hard to do.
right.
From the electrodes, you know, when we make materials, we're doing solid state reactions. You get micron particles, we grind them up, we make electrodes. It's more about how we make the electrodes than how we make the materials. Although with the sulfides, my student Steve spent a long time optimizing these sulfide syntheses, because you get, so when you make these materials, you seal them in an evacuated tube and you heat them up. If you have sulfur around, you're going to have some partial pressure of sulfur vapor in that tube. So you have to know, you have to control, you have to have a little bit extra sulfur to satisfy that sulfur vapor pressure. And you have to sort of keep your tubes the same size every time, so they have the same vapor pressure in the tube head space. So controlling like all of those parameters, the little excess sulfur that you need, the tube size, those types of things will play when we were trying to tune the stoichiometries like we were, that was a huge thing that we worked on. For normal materials where you don't really care like what your defects are as much, then you don't really spend a lot of time on it. But when we were trying to like exactly tune the vacancy concentration, the formal oxidation state of titanium, that became a really big part of it. Yeah, so you know, a little excess sulfur so you don't have anion vacancies.
Last chance for everybody in the room to ask a question if you want. No urgent questions anymore. Everybody looks happy. Well, then thank you to everybody online for joining us. Thank you again, Kim, for the wonderful talk.